Good morning. Today we're going to talk about NMR and IR, and the first bit here on NMR is the first thing you want to look at when you look at an NMR spectra, proton NMR spectra, is the number of signals. Sorry, white on white doesn't work. The number of signals, and this tells us how many different types of protons there are in the molecule. The next thing we want to look at is the position of the signal, and this tells us about the electronic environment of each proton. And if you have just an alkane, it's going to be down near 1. If you have a hydrogen on a carbon connected to a more electronegative atom, a hydrogen on a carbon, and it doesn't matter if it's a halogen or an oxygen, they're all going to be, or nitrogen, they're all going to be roughly 2 to 4, give or take a hair. Okay, now if there are 2 of them on there, that'll be more than that, but they're all in the region roughly of 2.5 to 4 for that hydrogen or hydrogens on the carbon with the more electronegative atom. Aromatic hydrogens are between 6 and 8.5. Okay, they're all very important. You'll see those a lot when you're looking at spectra, so make sure you look and realize what they're saying or what they're showing when you see one. Okay. The next thing we want to look at is the intensity of the signal, and the intensity of the signal, C here, tells us how many of each kind of proton there is. So we may be told it, or we may have to measure out the integration. Either way, we should be able to look at a spectra and tell roughly the number of hydrogens in each signal. And the last one, the splitting of the signal, tells us about the environment of the proton and how many hydrogens are on the adjacent carbon or carbons. Hydrogens on an oxygen, hydrogens on a nitrogen normally do not split the hydrogens on the carbon adjacent to it. So it's normally just hydrogens on the carbons adjacent to the signal. So in ethyl iodide, we'd expect to see 2 signals because we have the carbon on the right with 3 hydrogens on it and the carbon on the left with 2 hydrogens in the iodide. So this CH2 would be somewhere between 2.5 and 4, and the CH3 would be somewhere around 1-ish parts per million. The signal on the left between 2 and 4 would integrate for 2 hydrogens, and the signal on the right would integrate for 3 hydrogens. Okay, and that's just telling us how many hydrogens are on in that same equivalent signal. Okay, and then the last thing is the splitting. The CH3 here is next to a CH2, so it would be split into a triplet because there are 2 hydrogens next to it. And for the splitting, what you do is take the number of hydrogens on the adjacent carbon and add 1, and that'll tell you how much it would be split into. Okay, so try drawing these and thinking about how many signals are all drawn. You tell me how many signals you'd expect to see. Think about it, and when I'm done drawing them, we'll go back to the top and say how many signals. Okay, so ethane would have 1 signal because the CH3s are all equivalent. Propane should have 2 signals because the CH3s out on the end are the same, and the CH2 obviously is the same. Tert-butyl methyl ether, the CH3 on the oxygen would be 1 signal, and the 3 methyls on the T-butyl would be 1 signal, so it should have 2 signals. The 2,3-dimethyl-2-butene, all it has are 4 methyls. They're all equivalent because we have symmetry down the center of the molecule, and we have symmetry this way. So this would just be 1 signal. Okay, okay? And then Z, 2-butene, we have symmetry this way, so the hydrogens would be the same and the methyls would be the same, so 2 signals. And then E, 2-butene, we can rotate it. If we leave it in the plane and just rotate it 180 degrees, this methyl ends up down here, so it would have 2 signals. And then 1,4-dimethylbenzene has symmetry through the molecule this way and this way, so the methyls are all equivalent, and the CH on the ring, they're all equivalent, so this would have 2 signals. So here we have a spectra, and the spectra gives us the formula. So we see there are 7 hydrogens in the molecule. We have 2 signals. So with 2 signals, we have to have either a 6-to-1, 5-to-2, or 4-to-3 ratio of the 2 signals. If we measure this distance, the stair step above the peak, to this distance, the stair step above that peak, that's definitely not 4-to-3 or 5-to-2. So this is 6, this is 1. If you measure it out, this is about 1 centimeter, and this is about 6 centimeters. Well, granted, I'm rounding that a little bit because I don't have a ruler right in front of me to measure it, but that's roughly what it comes out to, and it is a 6-to-1 ratio. So in this 6-to-1 ratio, the signal at 2 parts per million has 6 hydrogens in that signal. Okay, so this is 6 hydrogens, this is 1 hydrogen, based on the integration, that measurement of the stair step for both peaks. Not the height of the peak. It has nothing to do with the height of the peak. It's just the height of the integration line above it, if you're given that. A lot of times you'll be given the numbers above 1 and 6 or whatever. So if you have the numbers, use those. If you don't, measure it out and see what you got. So then this signal, or this right here, is just this signal blown up so you can see what it is. It's a doublet. And then this is this blown up, and you see the 2 small peaks here and here, 2 peaks here and here, 2 peaks here and here, and then 1 in the center. So this is a septet, so 7 minus 1. This signal is next to 6 protons, and this doublet is next to 1 hydrogen, because you subtract 1 from the number of signals, peaks in it. So we have 6 next to 1 and 1 next to 6 with only 3 carbons, so it's going to have to be 2 methyls. This doublet that integrates for 6 is always this, 2 methyls next to a CH. And when we count that out, that's 3 carbons, 7 hydrogens. All we're missing is our iodide, so this has to be 2-iodopropane. The next one has 2 carbons, 4 hydrogens, and 2 chlorides. 2 carbon, if we figured out the IHD, which is just telling us the index of hydrogen deficiency, how many hydrogens are we missing in the formula? Do we have a double bond? Do we have a triple bond? Do we have a ring? We take the number of carbons, double it, and add 2, so we have 2 carbons. So 2 carbons times 2 plus 2 equals 6. Okay, we have 4 hydrogens and 2 chlorines, so we have 6 things. So our IHD is 0 because we're not missing any hydrogens. So we know we have 4 hydrogens, so we measure our integration of this peak to this peak. And with 4, since there are 2 peaks, it's either 3-to-1 or 2-to-2 for our integration. There are no other ways to split up 4. So this is definitely, this peak here is not the same height as this one here, so it has to be 1-to-3. So the signal at 2 here, this is it just blown up, is a 3 hydrogen doublet. So that has to be a CH3 next to a CH. Okay, then we see the CH down here at 6. It's at 6 because there has to be something moving it down there. The only thing that can do that is having both of the chlorides on the same carbon. So this has to be the 1,1-dichloroethane. The last one here on this page, C3H6Cl2, 3 carbons can hold doublet and add 2, 8. We have 8 things, so there are no double bonds, there are no rings. So we can draw it. We know it's a substituted propane because there are 3 carbons with no rings. There's no other way we can draw that. So then what can we put on that? Well, we know we have 6 hydrogens, so our ratio has to be either 5:1, 4:2, or 3:3 for our integration. This stair step is not the same as this stair step, so it's not 3:3, and this one at 4 is not 5 times the height of the one at 2, so it has to be 4 and 2. So the signal at 4 has to be 4 hydrogens. We can't put 4 hydrogens on. We can put 4 hydrogens on 1 carbon, but we'd have methane at that point, and there's nothing else we could have. So that doesn't get us anywhere. So they have to be on 2 separate carbons. So we're going to have 2 CH2s. Now those CH2s are a triplet. If we look at that signal blown up, so they have to be next to a CH2. Both of them, they need to be next to the same, or they need to be in the same environment. So they in this case, they need to be next to the same CH2, and it can't be themselves. So we have a 3 carbon chain with CH2s on each carbon. Then we look, why is the signal at 4 at 4? There have to be 4 hydrogens on a carbon with a chlorine attached to it. So the chlorines have to be on the end of the chain, so it has to be the 1,3-dichloropropane. And at this point in the class, this is in Org 1 that I'm making this video. We're not worried about the chlorides. We should be able to name, but as I go on, I'll name most of the compounds. And at this point in the class, we don't have to worry about naming the more intense and more harder problems. I'll just say them so we start hearing what they are. So if we go on to the next page, this is a problem out of a textbook, but we see that in it, the spectra are tabulated for us, not drawn out. So it gives us all the information written down in a little table, so we don't have to do anything else. We see the formula, C4H10O. We see that both signals are singlets, so both of them have to be next to no hydrogens. And we see the integration and where they are. So how can we get 9 equivalent hydrogens? We have to have 3 CH3s. Now there can't be a hydrogen on the adjacent carbon, so they all have to be connected to a carbon with no hydrogens on it. That's 4 carbons. We only have 4 carbons. We've used 9 hydrogens. We have 1 more hydrogen and we have an oxygen. So this just has to be the T-butanol. Okay. And as you're going along, draw the pieces out and then start putting them together. Don't try to put them together at the beginning. So the next one, C3H7Br, is a 6 hydrogen doublet. We've already said a 6 hydrogen doublet has to be a CH3 connected to a CH connected to a CH3. That's 3 carbons, 7 hydrogens. All that's left is a bromine. So this has to be 2-bromopropane, just like the one we worked earlier, except for it had a chlorine in it. And the next one, C4H8O, 4 carbons, double it and add 2, can hold 10 things. We have 8 on it, so we're missing 2, so our IHD is 2. Or, excuse me, divided in half, IHD is 1. So in this molecule, we better have either a double bond or a ring. If we look at the IR spectra, we have the big peak at 1720. We all know a big peak at 1720 is a carbon-oxygen double bond. So there has to be a carbonyl. That's our 1 IHD. So that leaves us 3 carbons and 8 hydrogens to place off of this carbon. So we look at this and we see the quartet and the triplet. Anytime we see a quartet and a triplet, the only thing that will give us that is an ethyl group. So there has to be an ethyl on one side of this. The other signal is a singlet for 3 hydrogens, so it has to be a methyl. So this just has to be 2-butanone. Okay. The next one, C7H8O, 7 carbons, can hold 16. We have 8. So we're missing 8 hydrogens in our, from what the number of carbons can hold. 8 divided by 2 gives us an IHD of 4. So one thing to think about when you have an IHD that high is it's most likely an aromatic ring. Okay, there are a few things that give us that high of an IHD. So we look in the NMR and we see a signal at 7, and signals at 7 are aromatic rings. So this just has to be an aromatic ring with 5 hydrogens on it and 1 group off of it. So that's 6 carbons, 5 hydrogens. That leaves us 1 carbon, which if we put the 3 hydrogens off of it, we'd have toluene, and there wouldn't be room for the oxygen. So it can only have 2 hydrogens on it. And then we have our OH, which our IR pointed to with this big peak at 32 to 3600. So that has to be benzyl alcohol. The next one has a 6 hydrogen doublet again, so that's 2 methyls next to a CH. Then it has a 2 hydrogen doublet, so that's going to have to be a CH2 next to a CH. We only have 4 carbons, 9 hydrogens. There's all our hydrogens, so all we're missing is our chlorine on there, and that's the 5th one. The next one, if we look at the formula, C15H14O, 15 carbons, double it, 30, add 2, 32. We have 14 hydrogens on it, so we are missing 18. Divide that in half, our IHD is 9. Why is it so high? There has to be something in this molecule that has a lot of double bonds or rings in it. So we look at the proton NMR. It has a multiplet at 7.25, so this has to have 2 aromatic rings in it. So if we draw 2 aromatic rings, don't connect them together because they're not connected together. They each have to have 5 hydrogens on them, so they have to be monosubstituted. So they're going to have to be connected to something else in the molecule. Then we see we have a 3 hydrogen singlet at 2.2. Okay, that's going to have to be a CH3 far away from everything else, so it isn't split by anything. And then we also see in the IR we have a carbonyl. So if we go back to our IHD of 9, 1 aromatic ring is 4, the other aromatic ring is 4, the carbonyl is 1, so 4, 4, and 1 is 9. That's our full IHD. So that takes us all of our double bonds and rings. So now we have 6 for 1 aromatic ring. For the other aromatic ring, 1 carbon for the carbonyl and 1 carbon for the methyl. So we are at 14 carbons, but we need 1 more. So there has to be another carbon. And we've used our 5 for 1 aromatic ring hydrogen, 5 for the other, and 3 for the methyl. So we've used 13 of our 14 hydrogens. We have to have 1 more hydrogen. So when we look at this, the aromatic rings are edge pieces. The methyl is an edge piece. The CH and the carbonyl have to be connected together because they're internal pieces. Okay. If we put 2 aromatic rings together, we just have biphenyl and we're done. If we put the methyl on a phenyl, we have toluene, we're done. We don't have room for all the other things. So the CH3 cannot be connected to the CH because the CH3 is a singlet. So the CH3 has to be connected to the carbonyl. That then makes the CH need both aromatic rings on it. So it has to be that. Okay. Now the next one, C4H7BrO2, tells us we have this in the IR, which that all points to a carboxylic acid. If we look at the NMR, we see a signal at 10.97 that integrates for 1. That is a carboxylic acid. So we have to have a carboxylic acid. That's our 2 oxygens. Then we have 3 signals, a triplet that integrates for 3. So that's going to have to be a CH3 next to a CH2. We have a 1 hydrogen triplet, and there we've used 3 carbons, so we only have 1 more carbon left. So it has to be a CH. It's connected to a CH2 because it is a triplet, and then it is at 4, so it's going to have the bromine and the carboxylic acid off of it. Okay, so that has to be that one. The next one, we have the triplet and the quartet. A triplet and a quartet tell us we have an ethyl group, so CH3, CH2. We don't even have to look further than that once we see the triplet and the quartet. And then we have that 5 hydrogen multiplet, so it has to be the monosubstituted aromatic ring. And we look at our formula, C8H10, 8 carbons, double it, 16, add 2, 18, subtract 10 from it. We're missing 8 hydrogens. Hydrogens come in pairs, so we divide that in 2, 8. That gives us our HD of 4, which gives us our monosubstituted aromatic ring. So on to the next problem. We have C4H8O3, so 4 carbons can hold 10 things, double it and add 2. We have 8, oxygen doesn't count, so we're missing 2, so there has to be an IHD of 1. We look in the proton NMR, we see a singlet at 10.95, and in the IR we see the proof for a carboxylic acid. So this has to be a carboxylic acid again. Then once we take out that singlet, we have 3 other signals, a triplet and a quartet, an ethyl group. Okay, the quartet is at 3.66. Why is it at 3? It's got to be off of an oxygen, so it has to be an oxygen, an ethoxy group off of something. And then we see we have a singlet at 4.13, which has to be a CH2 off of that, so it has to be the ethoxy acetic acid. The next one has a doublet and a septet. Doublet, 6 hydrogen, is 2 methyls off of a CH, and then the septet is the 1 hydrogen with 6 next to it, and then all we have left is the NO2, so this has to be isopropyl or 2-nitropropane. The next one is probably the hardest on this page because C4H10O2, the IHD is 0. We have a 6 hydrogen singlet, so there has to be 2 methyls that are equivalent, 6 hydrogens. They have to not be connected to each other because if they were connected together we'd have ethane and be done. So why are they at 3.25? They have to be off of an oxygen. If they were off the same oxygen, we'd have diethyl ether and we'd be done. We don't have that, so it can't be that. So we have to go on from there. So they have to be off different oxygens, so it has to be 2 CH3s off of an oxygen, and then we're left with 2 CH2s. So, and they're at 3.45, so they have to be off of an oxygen. So we have to have that, and then the CH2s have to be connected together because that's the only thing that needs one more bond. If we look at this, You're all sitting there thinking, but those CH2s are connected to a carbon with a hydrogen on it. Why are they a singlet? They're a singlet because they are in the equivalent to one another. They're in the exact same environment, and equivalent hydrogens do not split each other, so that's why they're two singlets. The next one, C5H10O, 5 carbons, can hold 12. We have 10, so we're missing 2. They come in pairs, so it's got to be an IHD of 1. We have a carbonyl at 1720, so let's draw a carbonyl. That's our 1 IHD. We have a 6 hydrogen doublet, which is a CH with 2 methyls off of it. And then we have a 3 hydrogen singlet, which would just be a methyl. So we have a methyl, we have a carbonyl, and we have the isopropyl. The isopropyl has to be an edge piece because it only has one connection. The methyl has to be an edge piece because it only has one connection, and we go from there. So it has to be the isopropyl methyl ketone. And then the last one, we have a multiplet at 7.35 for 5 hydrogens. Mono substituted aromatic ring because it integrates for 5. We have a 3 hydrogen doublet, CH3 next to a CH, 3 hydrogens next to 1 because it's a doublet. Now that's our 8 carbons, that's our 9 hydrogens, so the aromatic ring has to be off the CH. That leaves the CH with one more connection, so we have to have the bromine off of it also. Okay, and that's why the quartet, the 1 hydrogen quartet, is down at 5 because it's got the bromine off of it and the aromatic ring off of it. Both those move it to a higher number. 6 carbons. Hey, another problem here is we have the formula C4H9Br. We see 4 signals with an integration of this to this to this to this, so it has to add up to 9. 4 signals into 9. We see this is like 1 centimeter, this is like twice that, so this is a 1 to 2. Then this is like 3 of those first ones, and this is 3, so 1 2 3 3, which adds up to 9. So that gives us a nice splitting of all of the where the hydrogens are. So we have a 3 hydrogen triplet at 1, so that's a CH3 next to a CH2. We have a 3 hydrogen doublet at 1.5, that's a CH3 next to a CH. Now that's our 4 carbons, that's our 9 hydrogens. The only thing we're missing is the bromine. The bromine and the ethyl are edge pieces. The methyl next to a CH is an internal piece because it has 2 connections, so it just has to be the bromine and the ethyl on that 1 carbon. Okay, the next one, C3H4Br2, 3 carbons, can hold 8. We only have 6, so we're missing 2, so we have to have a double bond or a ring. We see signals at 6. 6 tells us it's probably a double bond, so it's going to be a propene. Now if we look at all 3 of these signals, they're all singlets. To be singlets, they would all have to have no hydrogens on the adjacent carbon. So that tells us this carbon right here, carbon number 2, can't have a hydrogen on it, but it needs one more connection, so the only thing it can have is a bromine. So we have to have a bromine on that one. Then we look at the signal at 6, and we're thinking, well, there's 2 hydrogens there at 6, so there has to be 2 hydrogens on our alkene. The only place they can go is here and here, and then we're left with 2 more hydrogens and a bromine, and those 2 hydrogens would be at 4 because they're next to a carbon with a bromine on them, or on a carbon with a bromine on them. So this would have to be that molecule so that everything was a singlet. The next one, C9H11Br. We look at that, C9H11Br, 9 carbons, doublet, 18, add 2, 20. can hold 20 things. We have 12, 11 hydrogens and a bromine. So we subtract 12 from 20 and we're at 8. Divide that in half. We're going to have a high IHD. 4. Whenever we see an IHD that high, the first thing that should come to mind is an aromatic ring. So let's draw an aromatic ring. Then we look at the 3 signals, and the first one is at 7.1 that integrates for 4.4. So those, since it's at 7, have to be the hydrogens on the aromatic ring. So we have to figure out what our ratio of these 3 signals is to come up with how many hydrogens are on our ring. So if we take 4.4 into 4.4, we get 1. 4.4 into 13, we get 3. 4.4 into 6.7, we get 1.5. Now we all know we can't have half a hydrogen, and 1, 3, and 1.5 doesn't add up to 11, so we have to do something to come up with that. So we have to double everything, so 2, 6, and 3. 2, 6, and 3 adds up to 11, so that's all our hydrogens. So the signal at 7.1 tells us there are 2 hydrogens on our aromatic ring. They're a singlet, they're equivalent, so that tells us our ring has to have some symmetry on it. So the hydrogens are going to have to be the same. Then we look and we see a 6 hydrogen singlet, so that's 2 methyls that are going to have to be the same. And then we have a 3 hydrogen singlet, that's 1 methyl. Okay. And then we have the bromine. So we have 2 hydrogens that have to be the same, 2 methyls that have to be the same, and then a methyl and a bromine that don't matter. So methyl on one end of the molecule, bromine on the other, and then so that we make it as sterically unhindered as possible, we need to put the methyls down by the bromine that are equivalent, and the hydrogens in between the 2 methyls. So that one would have to be this to have it work out. So here's 2 problems. This CH3 is next to 2, so it'd be a triplet. CH2 is next to 3, so it'd be a quartet. This one's next to none, so it'd be a singlet. The CH3 here on the aromatic ring would be a singlet. The OH would be a broad singlet because it's on the oxygen. They're normally singlets. Broad singlets because they're not normally split by the things next to it. This CH should be a septet, and this CH3 should be a doublet. So this CH3 is next to 1, so it's a doublet, and this CH is next to 9, so it's probably can't tell how many it's really next to, so it's probably a multiplet. And then this CH3 is next to 1 here, so it should be a doublet. Now down here below, the important things, this acetylenic hydrogen is probably 1.5 to 2. The aldehyde hydrogen is about 9 to 10. Okay. The methyl ketone is 2 to 2.7, and that goes for the CH2 next to the carbonyl. They're going to be between 2 and 2.7. Then the aldehyde is 9 to 10 here on this one. These 2 double bonds would be roughly 6 to 7, a little high for just a double bond, but it's conjugated to the aldehyde. This OH would be about 2. This CH2 between 3 and 4 because it's off of the oxygen. These 2 signals would be between 3 and 4. The CH would be okay. Then hydrogens on the alkene would be down in 4.5 to 6 region. The aromatic hydrogens off of the indane would be down about 7. These two CH2s would be about 2. This one would be a little less than 2. And then we have our 2 hydrogens on the carbon with the oxygen. They'd be about 3 to 4. And the 2 hydrogens next to the carbonyl, 2 to 2.7. Then we go down to the next problem. Gives us a formula C3H8O. We see the integration of 1, 1, and 3, 3, 6. So C3H8, 3 carbons can hold 8. We have 8, so there's no double bonds, no rings. So it's going to have to be a chain. Well, let's don't put the methyl hydrogen on just yet. So it has to be 3 carbons in a chain. And then we look and we see this 6 hydrogen doublet. So that's 2 methyls next to a CH. And then we have a 1 hydrogen split into a bunch. That's going to be the CH next to 2 CH3s, leaving us 1 oxygen and 1 hydrogen. The oxygen needs to be in between the hydrogen and the carbon, so isopropanol. So here we have C10H12O2. We see 5 hydrogens at 7.2, so that is a mono-substituted aromatic ring. We see 3 hydrogen singlet at 2, so that's a CH3, and then we see 2 CH2s that are both triplets. So we have to have 2 CH2s connected to each other, so they're at triplets. Okay, now C10H12O2, C10, double it and add 2, 20 plus 2 is 22. We have 12 hydrogens, we're missing 10, they come in pairs, so there has to be a double bond in this problem. Okay, we haven't used our oxygen yet, so it's probably a carbon-oxygen double bond. So then we see the methyl and the aromatic ring both have 1 connection. The carbonyl and the 2 CH2s have 2 connections, so they have to go in the center also. And then we have 1 more oxygen. So this is all of the pieces for the puzzle. And we see the methyl is a singlet. So the only things that would make it a singlet are being connected to the aromatic ring. Then you'd have toluene, you wouldn't have all the rest of it, so it can't be that. It could be connected to the carbonyl, so you have a methyl ketone, or it could be connected to the oxygen, so you have that little methoxy group. If the methyl, which is at 2, was connected to the oxygen, it'd be down past 3, so it's not connected to the oxygen, so it has to be connected to the carbonyl. The CH2 here at 4 has to be connected to an oxygen to be down that high. Then the other CH2 is at 3, connected to the aromatic ring, and then the oxygen's connected to the carbonyl. So if we draw it neatly, we have the phenyl, 2 CH2s, an oxygen, carbonyl, and the methyl. And if we knew more about the hint, 2-phenylethanol, that would be the oxygen, the 2 carbons, and the aromatic ring, and the acetic acid would be the carbonyl and the methyl. So the hint tells us sort of about it, but this being org 1, we haven't gotten into the reactions of carboxylic acids yet. So then we go on to how would we tell these apart? 1-bromopropane would have a CH2 at 3.5-ish, because you have the bromine around there. 2-bromopropane would have a CH there at 3.5-ish, because you only have 1 hydrogen on the carbon with the bromine. The aldehyde here would have that signal at 9 to 10, whereas this would only be at 2 for being next to the carbonyl. Here we have a methyl on a carbonyl versus a methyl on an oxygen. This would be 3 to 4. This one would be about 2. So that would be easy to see. And this one would have the 1 hydrogen, would it have a quartet and a triplet. and then it'd have a one hydrogen signal all by itself. So this would have 3 signals. This would just have one singlet because the methyls are the same. Okay, the next one, in new chemist in an industrial lab, oxygenated gasoline additives, so there's probably an oxygen in our molecule. We see a 3, a 2, a 2, and a 1. So we see a 3 hydrogen triplet here. So that's going to be a CH3 next to a CH2. We see a 2 hydrogen triplet at 4. So that's a CH2 connected to a CH2. It is at 4 because it needs the oxygen on it. So it has to have an OH. Now, when we look at this CH2 here, we're looking at from either side because we only have one other signal, this signal here. So this has to be just one propanol. And this CH2, we're just looking at it from either side based on the splitting of the small things. Because we can't really tell what this peak at 1.5 is split into. It's split into a bunch. Does it matter? No, because we can see everything about the molecule from the singlets, the doublets, the triplets. The easy stuff to tell what they're split into. So here we have a problem of 2-chloro-2-methyl-butane and doing an elimination on it. We haven't got to eliminations in Org 1, or it would help out a lot. But just looking at the spectra, we know our carbon framework for both answers has to be this. So all we have to look and see is what can happen in this reaction. So formula C5H10, 5 carbons can hold 12. We only have 10, so there has to be an IHD of 1 in our answer. We know our carbon framework doesn't have a ring in it, so our answers will not have a ring in it, so they have to have a double bond in it. If we look at our peaks, we have a 1:9 ratio, so our double bond can only have 1 hydrogen on it. So the double bond can only go here with the 1 hydrogen, and then the 9 being the CH3, CH3, and CH3. Now if we look at the next problem, we see a 2 to 2 to 3 to 3 ratio. So we have to have 2 different methyls because we have 3 hydrogen signals. We have a singlet, and we have what looks like a triplet, maybe. Okay, so we know that we have to have a 3 hydrogen signal next to something. So the double bond, it's not going to be this CH3 here, still next to a hydrogen there, because there wasn't a hydrogen there to begin with. All there was the chlorine. Okay, we're not going to move things around in a problem like this. So the double bond can't be out to, or can't be where it was in the first one, because it wouldn't look like this. So it can't be here out to the end carbon, because then you'd have 3 hydrogens on your double bond, and we only have 2. So that's not possible. Okay, so the only thing that's possible is to put the double bond here out to one of these methylenes. So we have 2 hydrogens on the double bond. We have a CH3 singlet, that's the peak here at 1.8, and then we have our, what will look like a quartet and a triplet. Granted that this signal at 2 is a nice quartet, the one at 3 is hard to tell, it's a triplet, but they're split together, so there have to be 2 carbons with hydrogens on the adjacent carbons. And the only way we can do that is this answer right here. So here we have the IR, the mass spec, and the NMR. The NMR tells us his signals are 5 and 2. The IR gives us this big peak at 2200, and the peaks here at 7 and 750. The mass spec tells us it's 117. Okay, so 117 with a peak here at 2200 must be a nitrile, because triple bonds are between 2 and 2200. That's 26. That gets us down to 91. 91, we said this was a monosubstituted aromatic ring, C6H5. So that's 77. So that leaves us with 14. So our formula has to be C8H7N. Okay. Now we know we have a monosubstituted aromatic ring because of this. We know we have a CH2 because of this signal here, and we know we have a nitrile based on the IR. The nitrile and the aromatic ring are edge pieces. They only have one connection. The CH2 has to be in the middle, so it just has to be this for our answer. Here we have a molecule that weighs 96. The only thing we really see is the 1685 carbonyl. Okay, and then we look at the proton NMR and we see 1, 1, 4, and 2. One number we don't see in that is a 3, so there are no methyls in our answer. Okay, there can't be because we have no 3 hydrogen signals. We have no 6 hydrogen signals. We need something that it would integrate for some multiple of 3. So we need to figure out our formula. It weighs 96. We know we have a carbonyl, carbon-oxygen double bond, based on that peak at 1700-ish. So that weighs 28. That leaves us with 68. 68, the maximum number of carbons is 60, or C5. That leaves us 8, or 8 hydrogens, to get us down to 0. So that tells us our formula, C6H8O, is our formula for this molecule. Okay, now 6 carbons, double it and add 2 is 14. We have 8, so we're missing 6 hydrogens. They come in pairs, so our IHD is 3. We know there's a carbonyl based on that in the IR. We know there's a carbon-carbon double bond based on these peaks down here at 7, 6 to 7. Okay, so we have to there's 2 of our 3 IHD, but there's no evidence for a third yet, so we need to keep working on it. So we know we have a carbonyl. The carbonyl is at 1685, which is really low for it's going to be a ketone because all we have are 1 oxygen in our molecule. So for a ketone to be that low, it has to be conjugated to a carbon-carbon double bond. So that leaves us 3 CH2s left. The 4 has to be 2 CH2s. It can't be a CH4 because that'd be methane and we wouldn't have anything left. So we have to have 3 CH2s. Okay. Now we said already there were no methyls in this, so the third IHD comes from a ring in the problem, and this just has to be 2-cyclohexenone. Okay. The next one, now this one I put in here because you can't really tell much about the problem. All you can see is the structure of the molecule and where the peaks are. You can't see what the peaks really look like. And the reason why I have this is I want you to look at the problem and see look for the easy things that tell you about the problem. Okay, so this one, the easiest thing to see is the integration is 2 to 3 to 3. So which of these, 1 propanol or 2 propanol, would give us 3 different signals with a 2 to 3 to 3 ratio? Okay, because it has to add up to 8 because both propanols have the same formula. If it were isopropanol, we have the 2 methyls that are equivalent, so there would be a 6 hydrogen signal. There is no 6 hydrogen signal, so it can't be this one. It has to be 1 propanol. In the next one, we see a signal at 4.5. Would this CH3 be at 4.5? No, that CH3 would be down there too because it doesn't have anything electronegative off of it. The only way we can get a signal at 4.5 is to have hydrogens on the carbon with the oxygen, so it has to be the alcohol. The next one we look at, we see a ratio of 1 to 2 to 3 signals. So which of these would have just 3 signals? This one, the hydrogens on this carbon, there is no other carbon that looks like that, so that's 1. There's no other CH2 with a methyl off of it, so that's 2. There's not another CH2 like this one with a CH2 and a double bond off of it. The double bond isn't symmetrical, and then this one, so this would have 6 different hydrogen signals. We only have 3. Can't be that one, it has to be this one. If we look at the second one, it has, we can rotate it, pick it up in the frying pan like a pancake, not flip it over, but rotate it 180 degrees, and we have the same thing. Everything is this, you have some symmetry in the molecule, so it only have 3 signals, so it has to be it. The next one, we see this peak at 11. It has to be a carboxylic acid. It can't be an alcohol. Okay, you don't need to look at all of the information in every spectra and dive deep into it to identify things. Look for the easy things to identify it and go. So here we have C4H9Br. 4 carbons can hold 10. We have 10, so there are no double bonds in any of these. So we have to look at our integration and see we have a 1 to 2 to 3 to 3, the stair step, 1 to 2 to 3 to 3. Sometimes it's given, not always, but you have to have 2 methyls. One, the first one is next to a CH2. The second one is next to a CH. There's 9 hydrogens. The CH has to be connected to the CH2. The CH, to be at 4, because it integrated for 1, it has to have the bromine on it. So it has to be 2-bromobutane. Okay, this signal is the most important one because it's at 4. It's the peak farthest to the left in the spectra. It's the one that has the electronegative atom off of it. So in the second one, this peak has the bromine off of it. This one has the bromine off of it at 3.5. Okay, so if we look at the second spectra, we see 3 peaks that have roughly the same integration and one that's like 1.5 of it. So it's going to have to be 2, 2, 2, and 3. So we're going to have a methyl. It's a triplet, so it's next to a CH2. We have this signal at 4. That's a CH2. It's a triplet, so it has to be next to 2. There's all our carbons. We just have to connect 2 CH2s together and put our bromine on the signal at the end of the chain, 1-bromobutane. And then that next one only has 3 signals with a 2 to 1 to 6. And remember, the signal at 1 is always going to be, almost always, usually, most of the time, maybe always, a methyl, or some multiple of methyls. Since this is 6 hydrogens, it has to be 2 methyls that are equivalent. It is a doublet, so it's next to a CH, and then we see that signal at 3.5, it's a CH2 that's a doublet, so it has to be next to a CH, and then it's at 4, 3.5, so it has to have the bromine on it. So 1-bromo-2-methyl-propane. Here we have a molecule that weighs 156. It has an ethyl group in it, quartet and a triplet, and the IR is utterly useless. So we know we have to have a CH3, CH2. That weighs 29. We look in the mass spec, we see 29 there. That leaves us 127. Okay, this is a molecule that doesn't split apart much. It has a very large piece that will not fragment in the mass spec. It happens to weigh 127. If we look in the periodic table, the only thing is it has to be ethyl iodide. It has iodide on there. Okay. The next one we see 180, 182. subtract 79 or 81 because they're of equal height. It has to be a bromine. It gets us down to 101. We see in the IR a carbonyl. That gets 28 off. That gets us down to 73. If we look in the NMR, we see a ratio of 1 to 1 to 1. So the number of hydrogens we have in our molecule has to be some multiple of 3 because it's 1 to 1 to 1. So we have to have at least 3, 6, 9, 300 hydrogens in this molecule. So if we did this, we'd get 73. That'd be 5 carbons, 60, and 13 hydrogens. 13 hydrogens is not divisible by 3, so that can't be our formula. So let's go back up. Okay. We have to have something other than carbons and hydrogens in this for the rest of the molecule. So if we look at the IR, we see the big peaks around 1200. That's probably an oxygen of an ester. Whoops. Put that 73 back there. Oxygen of an ester, that's 16. That gets us down to 57. Okay, 57 could be 4 carbons, 48, with 9 hydrogens. 9 is divisible by 3. So this, with 4 carbons, 5 carbons, C5, H9, O2Br, works for a formula for this molecule. So the signal at 1.2 is going to have to be a methyl. It's at 1. Okay, it's a triplet, so it has to be next to a CH2. We know we have a carbonyl from the IR, and then we also see, so there's 5 hydrogens used. That leaves 4 more for the molecule. This signal at 1.8, let's make it a methyl next to a CH because it's a doublet. Okay, there we have 5 and 4 hydrogens. We're done with all our hydrogens. So why is this signal at 4? What is that signal at 4? That signal at 4 is both the CH2 and the CH in the exact same spot. They're not equivalent hydrogens. They just show up at the same spot. So what could put this CH2 at 4? It would have to have an oxygen on it and connect that to the carbonyl. If the CH2 were connected to the carbonyl, it would be down at 2. It's not at 2, it's at 4, so it has to have the oxygen on it. Then that makes the carbonyl an edge piece and our bromine an edge piece, and so it has to be the bromine and the carbonyl on that CH. That would both put that just above 4 as it is, so this has to be our molecule. Okay. Here are some, unfortunately they're twisted on the page, but C4H8O2, so the IHD is 1. We see a quartet and a triplet. We don't see the integration. Do we need the integration? No, we don't need the integration because the quartet and a triplet is an ethyl group every time. So that leaves 3 carbons left for this signal right here, so that's going to have to be a methyl. Now why is that signal at 4? Well, it has to be connected to an oxygen. Now we know we have 4 carbons, 8 hydrogens, and 2 oxygens. So, and our IHD is 1, so we're going to have a carbonyl. So this one, for the CH2 to be at 2, it has to be connected to the carbonyl. The CH3 has to be next to the oxygen because it's down there near 4. Okay. Now if we look at the other one with the C4H8O2, it has an ethyl group again. So we have the CH3, CH2. The ethyl CH2 is at 4, so it has to have the oxygen off of it. The methyl is at 2, it has to have the carbonyl off of it. So it has to be that. And then the last one here is C4H8O, still has a 1 IHD, so you're going to have a methyl and an ethyl off of that carbonyl, so methyl ethyl ketone. Here we have compound weighs 86, and yes, the spectra are getting harder and harder to see in these, but it weighs 86. Okay. The IR has a carbonyl in it. That's 28. Okay. That leaves us 58. That would be C4, 48, and 10 hydrogens. And 5 carbons, don't forget this one, can hold 10 hydrogens and an oxygen with an IHD of 1. And we know our IHD has to be 1 because we have a carbonyl. So we have a carbonyl. And then if we look at the proton NMR, we see a 6 hydrogen doublet. We know a 6 hydrogen doublet has to be 2 CH3s off of a CH. And we see a 3 hydrogen singlet, and that's going to have to be a CH3. And then we count our carbons, that's 5 carbons, 10 hydrogens, and an oxygen. So the methyl and the isopropyl are edge pieces. The carbonyl has to be in the middle, so it has to be the methyl isopropyl ketone. The next one weighs 170, 172. Equal height, bromine, 79 or 81. Okay, that gets us down to 91. We see monosubstituted aromatic ring, C6H5, that's 77. That leaves us with 14. That would be a CH2. So we have 5 hydrogens there. That's our monosubstituted aromatic ring. We know it has to be an edge piece. We have the bromine. We know it has to be an edge piece. And then we have the CH2 in the middle. So it has to be this. This is a 2 hydrogen singlet. It's our C. This one weighs 154, 156. Subtract 35 or, nope, excuse me. Subtract 81, 79 or 81 because they're of equal height. So 154 minus 79, 156 minus 81 gets us down to 75. Sorry, I can't read. 136, 138. Thought that was wrong. 136, 138, 79 or 81. That gets us down to 57. That's going to be 4 carbons, 48, and 9 hydrogens. So our formula is C4H9Br. Okay, and then if we look at the NMR, we have a 6 hydrogen doublet. That's 2 CH3s next to a CH. We have a 2 hydrogen doublet. That's a CH2 next to a CH. We only have 1 CH, so they're both next to the same thing. And the only place our bromine can go is on the CH2. So here we have a 154, 156 for our 2 peaks. 154, 156. They're 3 to 1, so it has to be chlorine, 35, 37. That gets us down to 119. We know we have a carbonyl, so we subtract that. That's 28. That gets us down to 91. We have a 3 hydrogen singlet. That's a CH3. That's 15. That gets us down to 76. And we see the 2 doublets down there at 7. Then integrate for 2 each, which is a para-substituted aromatic ring, C6H4, 76. Gets us down to 0. So we have a chlorine, a carbonyl, a methyl, and a para-substituted aromatic ring. The carbonyl and the aromatic ring are internal pieces. They're going to have to be connected together. So then we can either put the methyl off the carbonyl or the methyl off the aromatic ring. The methyl off the carbonyl gives us a methyl ketone, and the substituted aromatic ring with the chlorine. That's going to be more stable than the other way around with the acid chloride, which we haven't talked about yet. Okay, now we're on to carbon 13. We won't use carbon 13 very much, but it tells us much the same sort of thing. The number of signals, how many different carbons there are, the positions. It goes from 0 to 200 in the carbon 13. And if we have the off-resonance decoupled spectra, it tells us how many hydrogens are on each carbon in the molecule. Okay, so we'll skip to the first problem. And in this problem makes it a little easier on us because it tells us the percentages of everything. So this molecule, which weighs 234, 236, or 238, is 30.5% carbon. 30.5% of that comes up to 72, so there has to be 6 carbons in this molecule. Okay, 1.7 of 234 gives us 4, so there have to be 4 hydrogens in this molecule. That's 76, so 234 minus 76 gives us 158. 238 minus 76 gives us 162. If we divide each of those in half, we get 79 and 81, which screams bromine to us. Okay, so this is telling us there has to be 2 bromines in this molecule. So I know you're all sitting there thinking, why is it a 1 to 2 to 1 ratio for that? Bromine's supposed to be 1 to 1. This is 2 bromines, so the first bromine could either be a 79 or an 81, and the second bromine connected to the one with a 79 could be either a 79 or an 81. The bromine 81 could have either a 79 or an 81. So the chances are we have a 1 chance of a 158, 2 chances of a 160, and 1 chance of a 162. So a 1 to 2 to 1 ratio for those, depending on the isotope. Okay, so we have to look at it and see, is it a 1,2 disubstituted dibromo compound, a 1,3, or is it a 1,4 disubstituted bromine? Okay, if we look at the NMR, we see 2 multiplets. We can't tell much about it, but they each integrate for the same amount, and there is no singlet, so it cannot be the 1,3. Now the 1,4, we all know there's symmetry down that. It'd be 2 doublets. But if the 2 bromines, since the 2 bromines are the same, all of these hydrogens are equivalent because we have 2 planes of symmetry. So this would be 1 singlet because all the hydrogens would be the same. This NMR is not 1 singlet, so it tells us this has to be it. And if we look at the IR, we do have that peak. It's 750-ish to tell us it's a 1,2 disubstituted aromatic ring. The next one we have is a weight of, pull it up so we can see it, 165, 120, 160, 120, 160, 200, so 165. Okay, so we know 165, sorry, changed page, I couldn't tell what happened. 165, it's 165, so that tells us there has to be a nitrogen. There's 2 peaks here, so it's an NH2. That's 16, 149. We know we have a carbonyl. That's 28, 121. We know we have a Paris substituted aromatic ring, 76. C6H4. That leaves us 21 and 24, 45. Okay, we see we have a 3 hydrogen triplet, which tells us there has to be a CH3, CH2. That's 29. That leaves us 16, or 1 oxygen. So our overall formula has to be C7, C8, C9, H5, 9, 11, NO2. So why is this signal at 4, this quartet? Well, it's at 4 because it has to have a CH3 connected to a CH2 quartet, and it's at 4, so it has to have our oxygen on it. We know we have an NH2 in the molecule. That's an edge piece. This oxygen is an edge piece. We have a carbonyl and a para-substituted aromatic ring. Okay, so is the carbonyl, the aromatic ring and the carbonyl have to be connected together. They're both internal pieces. So that makes this our last piece. So is it an amide or is it an ester? Our carbonyl is at 1700, so it has to be the ester with the nitrogen on the ring. So if we draw it out neatly, it has to be that with the ethyl ester. Okay, so we look at the and then the next one we have carboxylic acid. It weighs 200 or 202. Okay, it's a 3-to-1 ratio, so that screams chlorine, 35, 37. So that gets us down to 165. We know we have a, well, might as well take the carboxylic acid out. 45, CO2H, 120. We have a para-substituted aromatic ring, C6H4, 76. So that gets us down to 44. And then, what else do we know? We know we have a 3 hydrogen, we have a CH3 next to a CH. 2 carbons, 4 hydrogens, that's 28. And that leaves us with 16. 16 is going to have to be an oxygen to get us down to 0. Okay, so we have the acid, the aromatic ring, the methyl next to a CH, the chlorine, and the oxygen. The CH is at 4, so better put the CH3, CH off an oxygen. Okay, it's above 4, so it probably has the carboxylic acid on it also. Then we're down to just the aromatic ring and the chlorine. So it would have to be this one. The next one has a carboxylic acid, has 2 peaks at the M plus 2, which says bromine, has 2 triplets, so we have a carboxylic acid, which weighs 45. We know the 2 triplets have to be 2 CH2s, so that's 28. We know we have to have a bromine, that's 79 or 81, and the whole molecule weighs 152. So 79 and 45, or 81 and 45, is 19 off of that. 26, 126, and 28 gives us 154, which is the high one, or 79 and 45 plus 28 gives us 152. So here's our pieces. The CH2 has to be in the middle. Bromine and acid have to be an edge piece, so it has to be this 3-bromopropionic acid. And then we're down to this one where we see the M plus missing at 88. We see the alcohol, so 88 minus 17 for our OH. We know we have to have is 71. That could be 6 carbons. So, well, it can't be 6. It'd have to be 5, excuse me. 60 with 11 hydrogens to get us down to 0. So C5, H12O, IHC is 0. It works. We see in the carbon 13 we have 5 different carbons. We have, so all the carbons have to be different. So we're going to have a CH3 with a bunch of CH2s with an OH. There can't be any symmetry in this molecule. So this just has to be one pentanol. The last one here happens to weigh the same amount, has an alcohol, so it's C5, H12O, but we only have 4 different carbons, and we have this 6 hydrogen doublet, so it has to be 2 CH3s next to a CH. There's 3 carbons. We have 2 more, so they look like a 2 to 3 ratio, so it's going to be 2 more CH2s, because we have this 2 hydrogen triplet, which is the hydrogen on the carbon containing the OH, so it has to be this one. And as you go through this, if you have any questions, feel free to email and ask about them. Okay, have a great day. Bye.